Welcome again, STEM students. In Physical Quantities Part 1, we discussed the definition of physical quantity and expound the fact that physical quantity is represented by symbols, usually using English alphabet or Greek letters. For Part 2, we will explore the facts that physical quantity can either be fundamental or derived, as well as scalar or vector. Next description of physical quantity, which we will expound, is that physical quantity can be classified as fundamental or derived. What does fundamental mean? According to Merriam-Webster Dictionary, fundamental means forming a necessary base or core of central importance. It is synonymous to basic and foundational. That is why fundamental physical quantities are the basis for other quantities, which are collectively called derived quantities. There are 7 fundamental quantities, namely mass, length, time, temperature, amount of substance, electric current, and luminous intensity. Let us define each of them. Mass has the unit, or rather has the SI unit kilogram, which can be shortened into kg. You may be wondering what SI unit is. Don't worry, we will discuss about SI unit in the next lesson. Mass is defined by taking the fixed numerical value of the Planck constant h to be 6.62607015 times 10 raised to negative 34 when expressed in the unit Js or joule second. Mass tells you how heavy or light matter is. Basically, the amount of matter an object has. Length has the SI unit meter. It is defined by taking the fixed numerical value of the speed of light in vacuum, represented by lowercase letter c, to be 299,792,458, or as shortened, and as I have shared in our previous lesson in defining modern and classical physics, that is 3 times 10 raised to 8 when expressed in the unit meter per second. And length tells you how long or short. It also tells you how far or near an object is. Time. Time has the SI unit second, or S. It is defined by taking the fixed numerical value of the cesium 133 frequency, that is 9 trillion 192,631,770, or in short, 9 times 10 raised to positive 9 when expressed in the unit hertz, which is equivalent to second raised to negative 1. And time tells us or tells you the duration of an event or phenomenon. Temperature. Temperature has the SI unit Kelvin, or capital letter K. It is defined by taking the fixed numerical value of the Boltzmann constant, symbolized by lowercase letter k, to be 1.30649 times 10 raised to negative 23 when expressed in the unit joule Kelvin raised to negative 1, or joule per Kelvin. Temperature tells you how hot or cold matter is. More accurately, it is defined as the average kinetic energy of an object or matter. Amount of substance has the SI unit moles or MOL without the E. 1 mole contains exactly 6.02214,076 times 10 raised to 23 elementary entities. This number is the fixed numerical value of the Avogadro's constant n sub a, which I believe you have already encountered in your General Physics 1 lessons. It is expressed in the unit mol raised to negative 1, and it is widely known as Avogadro's number. The amount of substance uh, is the measure of the number of specified elementary entities such as atom, molecule, ion, electron, and any other particle or specified group of particles. Electric current has the SI unit ampere, or represented by capital letter A. It is defined by taking the fixed numerical value of the elementary charge E to be 1.602176634 times 10 raised to negative 19 when expressed in the unit C or coulomb. Electric current tells you or tells us how many charges are flowing per unit. Luminous intensity has the SI unit candela, shortened as CD. It is defined by taking the fixed numerical value of the luminous efficacy of monochromatic radiation of frequency 540 times 10 raised to 12 Hz. It is a measure of the wavelength-weighted power emitted by a light source in a particular direction per unit solid angle. Now that you know what fundamental quantity is, what do you think is its difference with derived quantity? Yes, you are right in thinking that fundamental and derived quantities are comparable to each other. As I have mentioned earlier, derived quantities came from fundamental quantities. A derived quantity is not a base quantity. It is the quantities which derived from the base quantities through multiplying and or dividing them. Example of derived quantity is speed, which is obtained by dividing the fundamental or base quantity length by the fundamental quantity time. For you to be able to comprehend how derived quantities are formed, let us dissect the statement derived from the base quantities through multiplying and or dividing them. This means that there are three ways in which derived quantities may be formed. Number 1, through multiplication. Number 2, through division. And number 3, through multiplication and division at the same time. Let me give you examples for each of the three ways. For multiplication, remember that length is a base quantity. When you multiply length by itself, it will result to the derived quantity called area. Area will now have a unit that is the product of the SI unit of length. Meter times meter equals square meter or meter squared. Length can be multiplied twice by itself, which results to the derived quantity volume. Volume will have a unit that is the product of the meter times meter times meter. And meter times meter times meter is equal to cubic meter. Electric current and time are fundamental quantities. When you multiply electric current with time, the result is a derived quantity called charge. The unit of charge is the product of the unit of electric current and time. That is ampere times second or ampere second. Sometimes, scientists rename units of derived quantities just like the unit of charge. Instead of saying ampere second, the unit of charge is renamed as coulomb, denoted by the uppercase letter C. The second way to get derived quantities is through division. When 1 is divided by the fundamental quantity time, the result is a derived quantity called frequency. The unit of frequency is renamed as Hertz or Hz, and that is equivalent to 1 over second. When length is divided by time, the result is the derived quantity speed. The unit for speed is meter per second since the unit of length is meter and the unit of time is second. Lastly, we may obtain derived quantities by both multiplication and division. Here are the examples. Force is a derived quantity which has a unit called Newton. Newton is actually equivalent to kg dot, or meaning multiply, by meter per second squared. This means that to derive the quantity force, we divide meter by the product of time with itself, that is second squared. Then as a whole, the meter per second squared will be multiplied again by kilogram. What are the fundamental quantities involved here? Those are mass multiplied by the length divided by the product of time with itself. Okay, next example will be work with the SI unit joule or J. Joule is obtained by multiplying kilogram or kg by m divided by s squared. After that, you need to multiply all those units by m. The fundamental quantities involved are mass, length, and time. And then our last example for this is the quantity power with unit watt. Watt is obtained by multiplying kg by m, and the m is divided by s squared. After that, you need to multiply all those collectively by meter, and then the final step for that is dividing everything by s. So the quantities involved here, which are fundamental, are the mass, the length, and the time. Moving on, physical quantity can be classified as a scalar or vector. When we say scalar quantity, it pertains to physical quantity that is completely described by its magnitude. Examples are volume, density, speed, energy, mass, and time. Scalars are described by real numbers that are usually but not necessarily positive. Very seldom, scalars can be negative too. For example is work, which is done on a particle by a force, and that is part of our discussion, future discussions in General Physics 1. Additionally, scalars can be manipulated or computed or solved by the ordinary laws of algebra such as addition, subtraction, division, and multiplication. No special mathematical rules are needed to solve for scalar quantities. Vector quantity, on the other hand, is a quantity that has both magnitude and direction. It is typically represented by an arrow whose direction is the same as that of the quantity and whose length is proportional to the quantity's magnitude. More information about this will be discussed in the next lessons. Examples of vectors are displacement, velocity, and acceleration. That was Physical Quantity Part 2. Up next is the discussion about units. Hope to see you again. Thank you and goodbye for now.